Now let's go for the CNN project. We're gonna do one Python project. We need a simple, a very basic convolutional neural network Python project. We are using CIFAR 10 datasets. CIFAR 10 datasets. It is the name of dataset. So we're gonna do a simple project based on these datasets. As usual, step number 1, import all the libraries. Import all the respective libraries for the CNN model. Import TensorFlow STF from tensorflow.keras. Import datasets, layers, models. Import matplotlib.pyplot_plt. Just import TensorFlow STF. This is the short form for the TensorFlow. You can give any name. It is just the short name, short form. You can give T, you can give TFS, you can give TFL. It is up to you. But once you use this, you can use this short form. You can use this short form throughout the project. Instead of writing this whole word, you simply write TF. And then again from the TensorFlow library, it is a library, remember, TensorFlow is an important Python library. And then from TensorFlow.keras, keras is the submodel of the TensorFlow. Import datasets, layers, and then models. Look, the CIFAR 10 dataset is a built-in dataset in TensorFlow, which exists inside the submodel keras. Just import these datasets from the keras. Import datasets and then layers and then models, because we need the CNN model layers by layers. And then import matplotlib.pyplot_plt. We may need to visualize the dataset. To do so, to visualize the dataset, import matplotlib. It is exactly like a matlib. Matplotlib is a Python library where we can use it to visualize the dataset. But there is a submodel which is pyplot. So matplotlib.pyplot_plt. Simply put plt. The short form of the pyplot is plt. You simply put plt here. As I told you, you can give any name. It can be pt, it can be pyt. It is up to you. Why we are doing this? We need this short form to use only tf or plt throughout the project instead of writing this whole word here. And this is the only reason that we need this short form, to save your time and make it simple. Step number 2, load and generate the data. In the second step, we are going to load and generate the respective data, which is CIFAR 10 datasets. So we can write train images, train labels, test images, test labels equals to datasets dot CIFAR 10 dot load data. Look, in step number 2, we are loading and generating the dataset. So we are taking train images and train labels, and then test images and test labels. Suppose train images is my input. This is the X value. Train labels is the Y value. Suppose, if you remember, in machine learning, we were doing X train, X test, Y train, Y test. So instead of X train and Y train, we are using train images and train labels. X train and Y train. X train was the input data, Y train was the output data. So here, for the X train, we are putting train images, because image is the input data. So it is my X data, and train labels is the output data. As we were using in the machine learning, Y train. Y train is the Y data. So for the Y train, we're using train labels, which is the output. And then similarly, test images, test labels, which means that X test and Y test. Input test data, output Y test data, equals to datasets.CIFAR10.load. We are using load data function. When you use this load data function, your complete CIFAR 10 datasets will be loaded with the help of this load data function. Now look at here. This is the dataset, and then there is a subterm which is CIFAR 10, and then .load data. So with the help of this one line of coding, your complete data will be loaded in your system. Look, it is the coding in Colab, taken from the Colab. You can try this coding in the Colab. You can try it in Jupyter. You can try it in the VS Code. It is up to you. You can use any editor for the Python language. It is a simple Python coding in the Colab, which is the online editor. The difference between the Colab, Jupyter, is the online status of the Colab. You can use Colab online. The other editors like Jupyter VS Code and others are offline. You can use them offline, but for the Colab, you must be online. Step number 3, normalize the data. What is normalization of the data? We need normalization of the data to put it in a single scale. We may have our loaded data into a different scale. There might be different scales in the loaded data. The different terms may be measured in a different scales. I repeat it, to bring all the measurements of the loaded data in a single scale, we do normalization process. So in the normalization process, we make all the parameters under a single scale. And that's the reason we do normalization of the data. It is not mandatory in each project of the CNN. There might be some projects where you need normalization of the data. So here in these data sets, we need normalization because different terms have been measured in different scales. So with this one line of coding in Python, we can write train images, test images equals to train images over 255.0, test images over 255.0. So there we did normalization to the data. As I told you, train images is like xtrain, test images is like xtest. So xtrain, xtest. Why not train labels and test labels? Why we are not picking train labels and test labels? Because remember, normalization you can do to the input data, not to the output data. Train labels and test labels are output data. So you have to do normalization only to the input data. In the input data, we have train images and test images. Because image is the input data, don't forget it. Image is the input data. It's like xtrain and xtest, which are input data. So we do normalization for both the train data and the test data. Now, if you see the pixels of the input image, like 8 by 8, 5 by 5, 2 by 2, there are total 255 pixels. Look, these 255 are the pixels of the image. So you just divide your train input data and test input data by the pixel values. Remember, pixels are the values in the matrix. If you see the matrix of the image, like 8 by 8, 25 by 25, 12 by 12, that values in the boxes are the pixels of the image. So you just divide your input data by the pixels values. I repeat it, we are only do normalization to the input data, not to the output data. Therefore, we are not taking train labels and test labels. We are only concerned to the train images and test images. It is like xtrain, xtest, ytrain, ytest. For the x, we put images, which is the input data. Because normally in the machine learning, we use x for the input data and y for the output data. So for the x, we have image here. Therefore, it is my input data. Train images and test images. Input data for the training and input data for the testing. Just divide both train images and test images. So this is called the normalization process. When you do this process, your all parameters of the image will come under one scale. So the previous issue has been over now because there are different parameters in the given data which have been taken with the different scales. We want to bring all of them under a single scale, and that's the reason that we are doing normalization step. Now when you run this step 3, your data will start loading. Look, the data is downloading from this website. It is a website www.cs.toronto.edu. It is a website. It is a website where these data sets exist. So it will start downloading from this data set. Step number 4, discovery of data. Here we need to check the data. I'm going to show you different classes of these data, which are class names, airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, truck. These are different class names of this respective data. You can discover it further. You can also go for the visualization of this data with the help of the matplotlib. We are going to play with the data, like you can discover the data, you can check. If you remember in machine learning, we were checking the rows, the columns, and other thing of the data. The same thing is happening here in step number 4. We are discovering the data. For example, here I want to check the class names. So the class names are airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, truck. Step number 5, create a CNN model. In step number 5, we are going to create a CNN convolutional neural network model based on this Cypher 10 datasets. So these are the lines of codes in Python language. Model equals to models.sequential, model.add of layers dot convolutional 2D of 32, 3, 3, activation equals to relo, input shape equals to 32, 32, 3, and then model.add of layers.max pooling with a two-dimensional of 2, 2, model.add of layers dot convolution of two dimension of 64, 3, 3, activation equals to relo, model.add of layers, max pooling of 2D of 2, 2, model.add of layers, convolutional of 2D of 64, 3, 3, activation equals to relo. Look, we are creating a sequential model. We already know that what is sequential model. In sequential model, we make model layer by layer. There is a kind of restriction. You cannot share a layer of a model with multiple layers, like with 3 layers, one layer with the 3 layers or with the 4 layers at one time, or with the 5 layers. But there is another kind of model which is functional model. Functional model is a bit in advanced level. It is more complex. You can share one layer with multiple layers in the functional model. For example, one layer in the model with the 3 layers, or with the 4 layers, or with the 5 layers. So it is more complex compared to the sequential model. We are using here a simple sequential model. Now after this, we are doing the feature extraction process. If you go back and check the block diagram of the convolutional neural network, there is a feature extraction phase, which is the initial phase. This one from here up to here, this is called the feature extraction. We are extracting the feature. We're using the filter or kernels, and then using pairing, stride, pulling to extract the important feature out of the input image. Exactly the same thing is happening here. We create the model, which is a sequential model, and then this is my first convolutional layer. I'm gonna add the first convolutional two-dimensional layer with the 32 filters. Remember, with the 32 filters, the kernel size is 3 by 3. There are total 32 kernels or filters with the dimension of 3 by 3. And then activation function equals to relo. Number of inputs, so the number of inputs are 32. This 3 is the RGB channel, which is the colorful. Like convolutional layer 1, for suppose this is my convolutional layer with the kernel. I'm using kernel here, and then pairing, stride, and then activation function. So here the total number of the filters are 30 with the 8 by 8 dimension. We did the same thing in the Python programming. We had a first convolutional two-dimensional layer where we are using 32 filters with a 3 by 3 dimension. The activation function is relo with the input shape of 32 by 32. This 32 by 32 is the input shape, the image input shape. There are total 3 inputs. And then we add max pooling two-dimensional layer. Add another layer which is the max pooling with the 2 by 2 filter. Here in the block diagram you can see here that we were adding the pooling here. It may be max pooling, it may be average pooling. So we have reduced the dimension from 8 by 8 up to 4 by 4 with the total 30 filters here. Do the same thing. Here in Python language, we add a max pooling two-dimensional layer where we are going to select the maximum value with a dimension of 2 by 2. So here the max pooling filter dimension will be 2 by 2. And then we are going to add another layer, which is a convolutional two-dimensional layer with the total 64 filters with the 3 by 3 dimension, and the activation function will be relo. Like here, this is my second convolutional layer with 60 filters having the dimension of 4 by 4. So here the filter, the kernel size is 4 by 4. There are total 60 filters, and similarly we are applying the activation function here as well. And then stride or maybe pairing, it depends on the model. Exactly the same thing is here. We add another convolutional layer 2 with the total 64 filters having size of 3 by 3 with the activation function of relo. And then again we're adding another max pooling two-dimensional layer with a 2 by 2 filter. Add another max pooling two-dimensional layer here. After convolutional layer 2, we are adding another max pooling layer, maybe max pooling and maybe average pooling. It depends on the model, on the CNN model that you choose. So sometimes you may need average pooling, sometimes you may need max pooling, but most of the time we are doing max pooling in CNN. So this is the another max pooling layer, again with the dimension of 2 by 2. And then if you want to add another third layer, you can also add another third layer. For example, convolutional layer 3 with a 64 filters and having dimension of 3 by 3, taking activation function equals to ReLU. And then also you can add another max pooling 2D layer and then another convolutional layer. You can add more and more. It depends on your model, what kind of model you want to build. So within these 6 lines of codings in Python, we have created a CNN model, a sequential CNN model with the 3 convolutional layers having activation function ReLU and with the 2 max pooling layers. Summary of a CNN model. Let me show you the detail, a summary of a convolutional neural network model here. What will be the summary? What is the detail of this convolutional neural network model? I'm going to use a function model.summary, so you will get this detail of the model. Model equals to sequential. There is a sequential model, and if I remember, convolutional layer 1 with a 3 by 3 dimension of 32 filters, and then max pooling 2D, and then convolutional layer 1 with 18,496 parameters. So you can see here the total parameters are 56,320. Trainable parameters are 56,320. Non-trainable parameters equals to 0. Now add some more dense layers to CNN. Remember, this is the fully connected layer phase. Here I'm gonna add some more dense layers to the convolutional neural network model, which is the fully connected layer. If you remember, we are going to flatten the final multidimensional array into a one-dimensional array, and then we will feed it to the dense layers, which is a fully connected layer. So with these lines of codes, we have flattened the multidimensional array into a one-dimensional array and then fed it to the dense layer using these 3 lines of coding. The model.add of layers of flatten. We are using flatten function in Python to flatten the final multidimensional array of the featured map into a one-dimensional array. And then we add another layer. It is a dense layer with total 64 neurons, and the activation function equals to ReLU. And then the final output layer, this dense of 10. So this is the final layer with the 10 outputs. Here with the flatten function, we have shifted this multidimensional array of the featured map, which is the final featured map of the input image, into a one-dimensional array. When you use the flatten function, it will shift it into one-dimensional array here, into a single column. And then this is the dense layer. This is the extra dense layer, which is the fully connected layer. So I'm going to add one dense layer or hidden layer with total 64 neurons and then with total 10 outputs. In the deep learning, there might be some steps which are not happening in the machine learning. For example, compiling of the model. We were not doing compiling in machine learning, in simple machine learning model. But here in the deep learning, we are doing compiling of the CNN model. To do so, I'm going to use this line of codes in Python language, which is model.compile of optimizer equals to Adam, comma loss equals to tf.keras, which is TensorFlow. Remember, tf is TensorFlow. Dot losses dot sparse categorical cross entropy from logits equals to true, and then comma matrix equals to accuracy. So we compile this model. With these parameters. Number 1 is the optimizer, which is Adam, and the other is the loss function. The loss function is sparse categorical cross entropy. And then the logits. This logit is also known as log odds function. It is a log odds function. It represents the probability values from 0 to 1 and then from negative infinity up to positive infinity. It's also called log odds function. And then the matrix parameter where we are using accuracy. What is Adam? Adam is the optimizer. We use Adam to update the weights of the model. There is another classical method which is stochastic gradient descent method. To update the weights. But instead of using stochastic gradient method, we are using Atom here to update the weights of the model. And then we are using sparse categorical cross entropy. This is the last function parameter. Sparse categorical cross entropy is more efficient when you have a lot of categories. If you have multiple categories, then you must use sparse categorical cross entropy. If you remember, last time we were using binary cross entropy. Binary cross entropy you can use if your category is in a binary form, like 0 or 1. So for the binary, you have to use binary cross entropy, but for the multiple categories, you have to use sparse categorical cross entropy loss function. It is the submodel, a subterm of the losses. So it is actually my loss function, sparse categorical cross entropy for the multiple categories. I repeat it, logit is log odds function, and also the matrix is accuracy. So we are comparing this model with these terms, Atom, loss function, and the matrix. Step number 7, training of the CNN model. Now in this stage, we are going to train this model, this CNN model. So with the help of this line of code, we have trained the CNN model. Suppose I give a name, history, to the model. It is a simple name. You can give any name. You can give history, you can give model, you can give M, you can give any other name. It is up to you. Or suppose I gave a name, history equals to model.fit of train images, train labels, epochs equals to 10, validation data, test images, and test labels. This fit is a function in Python language where we can train the model. So model.fit of train images and train labels. For example, look, we are training the model. So I'm going to pick the training data, not the testing data. I'm not dealing with the testing data. For the training, I'm going to pick the train data. Like if you remember last time in the machine learning, we were using X-train and Y-train. X-train is the input data and Y-train is the output data. Exactly the same thing is here. Train images is the input data and train labels is the output data. With the epochs, what is epochs? We have already discussed that what is epochs. Epochs is a complete cycle of a one forward and then backward propagation. So this complete cycle of a forward and then backward propagation equals to one epoch. I repeat it. One complete cycle of a forward and then backward propagation. This complete cycle equals to one epoch. And that is a validation data. Why we are using validation data? We are just using validation data to check that whether data has been cleaned or not. And that's the reason we are putting some extra part of the data, which is called validation data, to make sure that the data has been cleaned properly. So for the validation data, we are taking test images, test labels. Because remember, for the testing, we have to use test data. For the training, we have to use train data, not test data. These test images and test labels, we are taking for the validation data to check the cleaning of the data here. And then run this in Python language. Look, we have total 10 epochs, which means that there will be 10 cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 epochs means to complete 10 cycles. Within these 10 cycles, the model will be trained. Remember, we have already covered this thing in the theory, that how forward and backward propagation takes place. During backward propagation, the weights and the bias values update accordingly. So it depends on the output. It may take 10 repetition, it may take 100 repetition, which means 100 epochs, or maybe 1000 epochs. It depends on the complexity of the model. The more the model is complex, the more epochs will be needed. It depends on the model. So during forward and backward propagation, forward, backward, we continuously update the weights values and the bias values to train the model to get the accurate output. So exactly the same thing is happening here in the Python language. If you have 100 epochs, then this number of repetition will be up to 100. If it is 1000, from 1, 2, 3 up to 1000 repetition will take place here. But since we have only 10 epochs, therefore I have 10 repetitions, 1, 2, 3 up to 10 here. Step number 7, final output of the CNN model. Now I'm going to show you the final output of this convolutional neural network model. So in Python, we can write test loss, test accuracy equals to model.evaluate of test images, test labels, verbose equals to 2. Look, we are evaluating the model. We have created the model, we have trained the model. Now it is the final stage, the final phase to check the model, to check the output of the model. So I'm going to check the accuracy of the model. Therefore, I'm using evaluation function. Test loss, comma, test accuracy equals to model.evaluate of test images, comma, test labels. Remember, we are testing here. We are checking the final output here. So I'm using test images here. Test images to evaluate the model, to make sure the accuracy of the model. Remember, we are checking the accuracy of the model. To check the accuracy of the model, we need to use the test data, not trained data, test data. In machine learning, we have studied that we put some percentage of data for the testing phase and big amount of data for the training phase. So for the testing phase, why we need testing phase? We need testing phase to test the model finally, that how accurate our model is. And that's the reason we allocate test data separately in a small amount. Now we are picking this test data to check the accuracy of the model, to check that how our model is accurate. Therefore, I'm picking test images and test labels, which means that X test and Y test. Test input data, test output data. When you use the accuracy function, just take a print of test accuracy, you will get almost 69%. So my model is 69% accurate, which is not very good, remember. 69%, it's still good. It is not bad, but it is not very good. You need to try to make it more and more accurate. You can add some more parameters, you can change some parameters as well in this model. And there might be a stage where you may get it 90+%. So just play with the parameters, play with the model, you will improve the accuracy level. This is the accuracy of the level. We have tested the model with the help of the test data using evaluate function for the model. So when you take the print of test of accuracy, remember, take the print of test of accuracy, we got 69% accuracy. 69% is not very bad actually. It's still better, but not in a very good condition. We have to try to make it more and more perfect. You need to try to get it 90+% accuracy, where the model will be in a very perfect condition. So that's the end for the CNN section.